Hello, Chemistry 11 honors. Today we're going to talk about calorimetry. And what is calorimetry? It is an expansion of how do we get the values for delta H. Now, recall in last days, we talked about delta H, and what is delta H is the change in energy or change in enthalpy. So how are we able to gather that data? And one way is through calorimetry. So delta H can be determined experimentally by measuring the heat flow of a reaction at a constant temperature. That measurement of heat flow is called calorimetry, and the apparatus that measures the heat flow is called a calorimeter. Now, there are generally two types of calorimeters that are used. One is called a constant pressure calorimeter or a coffee cup calorimeter. And this is a reaction that occurs at atmospheric pressure. It is assumed that the calorimeter prevents the gain or loss of solution heat to the surroundings, and the heat gained by the solution must come from the reaction. So how do we set it up? It's basically two coffee cups put together to form an insulation. And then what happens is the reaction occurs inside, and we measure the temperature. Now, the key thing that you should be aware of is, again, remember, what you have is the heat of the reaction is equal to the negative heat of the solution. Okay? This goes back to the beginning of our notes when we talked about thermodynamics. Remember, we talked about, not here, work and heat. I think at the very beginning. Q system is negative Q surroundings. Okay, now, so let's take a look at a question. It says when 50 mils of 1 molar HCl is reacted with 50 mils of 1 molarity NaOH, the solution goes up from 21 degrees Celsius to 27.5 degrees Celsius. Calculate the delta H of the system. Now, the first thing is you recognize is that this is a neutralization reaction. So we have HCl and NaOH gives you NaCl and H2O. And what you have here is the number of moles. So you have 50 mils here, you have 50 mils here, you have 1 molarity here, 1 molarity here. So you have 0.050 moles. You also have 0.050 moles. Okay. Now, the one thing in the back of your mind you have to remember is recall Q of the system is negative Q of the surroundings. So if we were to set this up, remember delta H is talking about the system. So Q of the system is equal to negative Q of the surroundings, which is M times C times delta T. Now, where do we get the mass? If we look further in the question, it says assume the total volume of solution is 100 mils, and the density of the solution is 1 gram for every mil. So I would have 100 grams times 4.18, okay, times my delta T in this case, which is 6.5 kelvins. Now, why did I change it to Kelvin? Is because I have the units of Kelvin in my specific heat. Now, in this particular case, recall, since I'm looking at the difference in the temperature, doesn't matter if I use degrees Celsius or kelvins, the difference is exactly the same. So if I have 100 times 4.18 times 6.5, I get an answer of 2717 joule. Now, you might say, well, how come the answer is different? And the reason being is I'm looking for delta H. Okay, so delta H, recall from last day's notes. If we scroll down to the, let me get my question. Delta H is per mole of reaction. So in this particular scenario, what I would need to do, the second part, is for delta H, I would use, whoopsie, I forgot the negative here, negative 2717 joules divided by the moles of reactions used, in this case, 0.050 moles. And that would give me an answer of negative 54340 joules. Okay. Now, the second type of calorimetry is called a constant volume calorimeter or bomb calorimetry, and generally used for combustion reaction. So in a reaction, there's a steel bomb, that's what this little thing is. And there's a combustion that takes place, and this bomb gets heat up, and this heats up the liquid in the calorimeter, which is right here, if we can't see it. Okay. Now, because it's in a bomb, one needs to determine the heat capacity of the bomb as it transfers the heat. Now, notice I've given you a series of 4 equations. These all derive from the Q reaction is equal to negative Q surroundings. In this case, the surroundings is the entire calorimeter times the delta T, the change in temperature. Now, here it's broken down into, because remember there's the bomb and the water, so this is broken down into how much heat the bomb has and how much water the bomb has. Now, recall, how do you calculate heat? Is you multiply it, the heat capacity times delta T. And the heat capacity, remember, can be determined by specific heat capacity times the mass. Okay, so these 4 equations are all related. So please make sure you understand how these are all related. Okay. So let me give you an example here. It says a 2.2 grams of sample quinine is burned in a bomb calorimeter whose total heat capacity is 7.854 kilojoules per degree Celsius. The temperature of the calorimeter increases from 23.44 degrees Celsius to 30.57 degrees Celsius. What is the combustion per gram of quinine? Now, again, we go Q reaction is equal to negative Q surroundings. Now, in this case, remember the Q surroundings, if we look at the top, is equal to, is equal to the C of the calorimeter times delta T. So in this case, it's negative 7.854 times delta T, which is 30.57 minus 23.44. So if we do that, 7.854 times 30.57 minus 23.44, I get an answer of negative 55.99 kilojoules. Okay. Now, if I want per gram, then what I would do is I would take the negative 55.99 kilojoules divided by 2.20 grams. divided by 2.20, and that would give me negative 25.5 kilojoules per gram. Okay. Now, notice in the questions, I started with the Q reaction is negative Q surroundings. Okay. Even in this previous question here, I used Q system is negative Q surroundings. So my suggestion would always be take a look, start with that, so that you don't get confused with the negative and what you are trying to determine. Now, if you take a look in your textbooks, you look on page 250, okay, and page 200 to 254, what you will see is they talk about calorimetry. They do talk about a coffee cup calorimeter and how it works, or a constant pressure calorimeter. And they give you a worked example here on page 252. And then what they do is you scroll down is they take a look on page 253, 254. They talk about a bomb calorimeter. All right, so my suggestion would be go through these pages in your textbook to sort of get an idea of the concept behind it. What I do is I just sort of give you the basic bare bones, but my recommendation is definitely do read over the stuff in the textbook for more details. All right, folks, thank you very much. Have a good day. Bye-bye.